to the serious stuff, right? So we are an open source vector database. And one thing that you might have heard of vector databases is they kind of came into prominence and people started to use them because of the vector embeddings coming from machine learning models. And I'm working on this stuff for a long time already. So next year is going to be my 10th anniversary working with vector embeddings. So I started all the way back with something called Glove, which are like tiny word embeddings, right? But there's like, you know, that if you had like the word seal and then it says like, you know, that's close to Korea. So the tiny language models, if you will. And then all of a sudden that grow into what it is today. But there's something important because this is not just any database, right? Something new is happening. And if we quickly look at the history, right? So we look at the old systems, the ways how we built database back in the days, right? You had Oracle and IBM and these kind of databases. And out of that, when the internet started to emerge, people started to use SQL, open source started to play a role, right? Nobody thought that would happen. With Postgres, MySQL. And then we got the mobile wave, right? So we're amazing companies. All the companies in there, like Redis, Hadoop, MongoDB, very important companies in that space. And then we got, of course, the cloud with the famous players in the cloud. And the question always was, with machine learning, is that just a little bit of cloud and a little bit of mobile? Or is it something new? Is the AI thing something new, right? And so we believe, of course, that is new, and then I'm going to explain to you why. But in a nutshell, the reason why we believe it's new is because the big difference between adding machine learning or AI capabilities to what you're doing is that if you make something what you see in the top called AI native, means that if you take the model out of the application is gone, right? So what you see happening there on the left-hand side, or for you on the right-hand side, that's AI native. We cannot do that and build those kind of applications without AI. So that's the term, AI native. And Weaviate is an AI native vector database, or an AI native database, if you will. And so what we're doing is that we're creating this ecosystem, right? So what you see, let me go to the screen, let me show you. So we have here, we have the frameworks of the LLMs, right? You all know the LangChain, the Llama Index, and that kind of stuff, right? The model providers ranging from OpenAI, Cohere, and those kind of models, but also open source models. I mean, today we saw a lot of interesting Korean models, right? So all that kind of stuff that's happening. The container infrastructure, data pipelining, and of course the hyperscalers, you know, meaning the big cloud providers. And we sit in the middle, right? That's what we focus on. And that is the ecosystem that we're building around the database. So what it basically does is very simple, right? So we take any type of multimodal data. So what we mean with multimodal is not only text, it can be images, it can be audio. You create an embedding, right? The vector embedding, you store it in the vector database. And the reason why that's new is that we can now find things on more than just keyword search. We can search images, audio, the meaning of text, and those kind of things, these vector embeddings. And these vector embeddings are everywhere. So if you are very knowledgeable about models, and if you dig into how they work, the vector embeddings everywhere, right? So, what do we do at Weaviate? So the core of Weaviate is open source. And it's going to stay open source, and that is just the database. And the database, out of the database come a bunch of APIs. So everybody can use them, doesn't matter where you are. You can interact with the APIs with Python, TypeScript, and what have you. But we start to now also build our ecosystem around it. So one of the things that we're doing, and I'm going to give you an example of such a video today, is that what we call the educational part, right? So we believe, so how many people in here are developers who write code? Who's writing code? Not now, but I mean like for work. Nobody? Yeah, a couple, yes, hands, thank you, great. So if you write code, right, we help you to understand how to do this, right? Because writing for AI is new. And so we have knowledge, and you guys are actually building it and bringing it to our users and our customers. So we help through education. And I'm going to give an example of that, right? And you have deployment, options, right? So what we see nowadays, so we have like serverless, which is just you go sign up and you're good to go. You have the enterprise cloud, which for the big enterprise load, and we have bring your own cloud, which means that if you want to run with your customers inside the VPC, you can do that too. The integration, well, that was what I just mentioned, right, with the embedding models. And then we have something that we call the workbench. So the workbench focuses on helping developers, right? So tooling, right? So the tooling can be the clients, can be the graphical user interfaces, the apps. You can edit the database. And operations could mean like you have certain services for operations inside the database. So all this together, this is the ecosystem that we're creating and that everybody can use based on the open source database. So that's what we do and what we focus on. And this is kind of the trajectory that we're seeing. So everything started with a vector search. So we got these vector embeddings from these machine learning models. Doesn't matter what kind of machine learning model is, all of them produce vector embeddings, and we could do better search and better recommendations. But the thing was with vector search was that for us as a database company, that was amazing and a lot of people loved it. But it was kind of, it was better. It was not newer. It was like better. And then RAG emerged. And RAG is the term that is like an abbreviation. So RAG stands for Retrieval Augmented Generation. And what it basically does, if you want to build your own agents, and if you want to build your own search integration with chatbot applications, generative applications, and those kind of things, you need a combination of the model, the machine learning model, AI model, and the vector database. And that's basically what RAG stands for. But out of RAG, something super exciting came. Because you see, RAG is just one-way street. So you have a query, goes through the vector database, results go into the model, presented to the user. But what we could also do is store that information back into the database. So if you have some time left, just now, then I can give you a demo where you can see how that works. So that's what you kind of see here, right? So started with search, with RAG, we got the chatbots, Q&A systems, co-pilots. But now the new thing is like the generative feedback loops, right? So even with like data cleansing and those kind of things. So let's say that you have a data set, and you give the instruction to the database where you say everything stored in the database should be in Korean. So if you then store something in English, it just translates it for you. You don't have to do that anymore, right? So that's like a complete different paradigm, right? So it's like it's not doing that stuff yourself anymore. It's now changing in the model sitting in between you, the user, the developer, and the database. So, well, this is kind of like a recap of what we talked about, and I think the most important thing to talk about is like maybe the third as well, but that's the first one, right? So we focus on making it for developers as easy as possible to build AI applications, because it's not easy, right? You need to learn how the models work, how to operate them, how the database works, how everything works together. So we try to help there. And again, I'll show you an example in a bit. And the thing is, like, we're like agnostic, what you see here, from how we deploy these kind of things. Why? Because everybody wants to use a database in a different way. And thanks for the database being open source, it makes it easier to do that. So I'll get back to the demo, so I'll skip this over when I have time left. But one of the things that I want to show you is that about the education part is this kind of stuff, right? So we were working with the community, and one of the things that came out of the community was that question. Let me. So. So one of the things that came out of that was that we got, like, from the community in Korea, we got a question where they said, like, hey, this is all great that we can now do vector search. It's great that we can have like multiple indices in the database. That's all great, but the models and the database don't work very well for Korean language, right? So how do we do localization? So then we work together with the community and with the users here in Korea to actually build that. So this is an example of, like, this is JP, and JP, he works in our developer relations team, And then when our team develops it, this is the kind of stuff that we make. So just want to show you this example. I hope everybody can hear it. So here we go.
Hi, my name is JP Huang. Let me tell you about some of the things that you can do with Weaviate and Korean data. Weaviate includes powerful integrations that help you to build amazing AI apps with Korean data. Now, that includes integrations with multilingual models like those from Cohere. It might be for creating embeddings, or it might be for large language model integration as well. And now we've added a Korean tokenizer to use with Weaviate. Tokenization is the act of breaking up sentences into smaller parts. Now, this is relatively easy with Western languages like English or French or so on. But for Korean, as you know, this can be more complicated. Korean doesn't rely on spaces, so breaking up a sentence like 아버지가 방에 들어가신다 can be quite complicated. Now, in Weaviate 1257, we've added a Korean tokenizer that can split Korean sentences into words, so that you can perform searches using words like 아버지, or 방, and so on, not wrong words like 가방. I've created a short demo of how to use the Korean tokenizer with Weaviate. You can simply follow this end-to-end and see the Korean tokenizer in action, from connecting to Weaviate all the way to setup, ingesting data, and how it works. And by the time you're done with this example, you'll have performed keyword searches, and you'll even perform retrieval augmented generation as well, and briefly discuss generative feedback loops. And when you're done, you can try out the Korean tokenizer and also other Weaviate tools through our documentation. Thanks very much.
So this is an example where you see how we work together with the community on building extensions on the database for, in this very specific use case, the Korean tokenizer, right? And everything that, and everything that we create ends up in that open source ecosystem, and and then is distributed to everybody else. So a couple of things. Some people are like excited about what's happening now in the database. So this is for the people in the audience who are like really database nerds who like that, right? So one that I really want to double click on. Let's see if there's more. Yeah, I'm going to go for the first one. That is the tenant offloading. So one of the things that we see that when these use cases become bigger, right, and you want to store them, and you keep everything in memory, that's very expensive, right? So because memory is the most expensive besides CPUs. So what we now have is that you can offload the data to your disk, or you can offload it to storage buckets. So for example, if you run on Amazon, on AWS, you can offload it to S3. And that's all just with a simple API call. So you can build these huge use cases with the vector database and your models, and just with an API call, you can offload it and what have you. And then for the rest, all the other things that you see is just, we keep updating and making everything in the database better, more optimized, and more importantly, more easy to use. Because again, it's a big database. So I think also looking at the time for now, I'm going to leave it at this one. But what I'm going to do is that on the website, everything that you've seen about us, if you want to play around with these data set, everything is open source. We got to do a couple of more also, release some Korean data sets. But the first one that you saw from JP is already live. So if you just Google or something for Weaviate Korean tokenizer, you'll find it. And we would love to hear from you. How are you using it? How is it working? Is it helping you in building your applications? So again, thank you so much for having me, for listening. And well, I hope to see you next time. Thank you.
네, 저희가 시간이 조금 남아서 질문을 2개 정도 받아보려고 하는데요. 네, 저희 질문이 있으신 분들은 손을 들고 질문 주시면은 저희 귀여운 베슬 굿즈도 함께 드릴 예정입니다. Thank you for your presentation. So we'll now take about 3 questions. So if you have any questions, please raise your hands.
네, 그러니까 AI based, I mean AI native 의미를 정확하게 알기 위해서 노력하고 있는데요. 네, 네. 네, 맞아요, 맞아요. Yes, and 그렇게 들었을 때는 그 전통적인 그냥 벡터 DB, 그러니까 벡터 데이터를 저장하고 벡터 데이터를 의미 있게 쿼리해 나가는 것 말고 그 외적인 것들도 있을 거라고 저는 그냥 상상이 돼가지고요. Okay, I expect there would be more features other than just storing, just vector data or just querying relevant vector data because, there are a lot of solutions just doing that. So yeah, because you said, AI native storage, so I expect something there would be more. So especially for the people who are engaged with the AI modeling or serving AI models, stuff like that. So 여기까지 얘기했을 때 제가 생각이 나는 건 feature store거든요. Do you insist that the purpose of the Weaviate would cover some of the features of feature store or 아니면은 그 feature store와 Weaviate의 그 관계가 뭔가 있다면 혹은 설명해 주시면 감사하겠고 그러니까 그 ordinary vector store 말고 다른 차별점이 있다면 그것이 무엇인지 그게 궁금한 점입니다. 네. Thank you.
No, that's actually really good English. So thank you. No, so this is an excellent question, right? So let me answer this also for the people in the room with like a little bit of like history. So the vector embedding. So the way what you do with the vector embedding is they're just distances. So what you do is you compare distances to each other, right? So let's say that you have 10 documents with a vector embedding, 10 vector embeddings, and you have a query. It's also a vector embedding. And then you compare the first to the first, so the query to the second, the query to the third, etc., etc., etc. Doing that is in itself simple, right? It's just a comparison. So that is what we call like the brute force comparison. So that's how it started. But the problem that started to emerge was like if you do that, if you have 10 documents you want to compare to, then if you do 20, it's twice as slow. So if you have like a billion or many billions, it takes hours to get to a result. So the first step that came, and that mostly that work came out of like Spotify, Facebook, etc., was something called approximate nearest neighbors, where people said we have new algorithms that by giving an approximation are still super fast, even for billions. So now we could do that super, but the problem was that the first of these algorithms, you needed to build an index, and then if you had the index, you couldn't update it, you couldn't delete anything, those kind of things. So the first step that came for the vector database was we're gonna make sure that we're good at storing these embeddings at scale, right? And now a lot of databases support some form of embedding search. That was what you were referring to, right? So now the first differentiator between the existing databases and the new databases is just about scale and ease of use. So if you use search engines that are very well known, it's sometimes harder to do vector search on a large scale. So getting to 1 billion is almost impossible. So that's the first use case. And the second one is that when you look at the search cases, is that the ease of use of actually doing vector search. What then happened was that we learned that especially for text, pure vector search is often not enough. So you want to do something called hybrid search, where you mix different indices. So something like a so-called BM25 keyword index with the vector index. That's the reason why Weaviate has a built-in Korean tokenizer. If we would not have hybrid search, we would have not needed this. So now the database like Weaviate has this additional unique feature where we're saying like, hey, you can do hybrid search. And out of that came the ask from a lot of users where they said, well, it's all great, but if I store all these vector embeddings in memory, that is very expensive, like very expensive at scale. So can you guys build something where you can offload this to S3 buckets and organize this better? So we said, yes, we can. So what now started to happen was that we had these filters, the data object storage, the ease of use to the clients, and those kind of things. So that by the time you build a production case with vector embeddings, you need all these features. And there's just a small set of databases right now that offer all these features. And I believe that it's fair to say that with the offloading of the tenants and those kind of things, Weaviate is even unique. Now, the last thing what you said about the feature stores have a slightly different use case. So the feature store is more for labeling, right? So if you say, I want to label a lot of data, I store the features in the database, which is the feature store. So that is not the same as the vector database, because the vector database really focuses on doing high quality similarity search in the vector. So the feature store has a different use case, but long story short, you can build your applications, AI applications, end to end on top of something like Weaviate, and you can do that with others. Very last thing, you asked about AI native, and that's what I heard in your Korean question. So let me one more time to make sure that the definition is clear. So what we mean with AI native is an application in which the machine learning model is crucial. So if we take out the machine learning model, the application dies. That's AI native. If you have an application where you add a little bit of machine learning, it's more AI enabled. It's not AI native. So, and that first use case, where that model plays a crucial role, that is that we aim to deliver with Weaviate, and as easy as possible. And with that large feature set that I just mentioned for production cases, I believe that right now we're, if not the only one that has all these features available for hybrid search, for tenant offloading, for model integration, data storage, data filters, and so on and so forth for your use case. So I hope that answers the question.
Hi, my name is Kevin. I have a question about what's Weaviate's future plan for hardware acceleration, because I've heard recently, companies like Jilly's, they recently launched like a collaboration with NVIDIA's GPU in terms of acceleration for vector operations. I know LansDB is doing something with their CPUs using SIM. So what future plans or anything on the roadmap do you have? If so, maybe you can share some details about that. If not, is that something you're looking for in terms of opportunities?
Thank you. That is a really excellent question, and that's a very detailed question. So doing vector search, you can use two types of chips, right? So you can use CPUs or you can use GPUs. So let me first start with the CPUs. So like the SIMD enablement, that's all also in Weaviate. So if you just Google, so the whole SIMD optimizations are written all the way in assembly in Weaviate. So that's all there. If you actually Google for Weaviate SIMD, you'll find it. But we also did a lot of work together with Intel. So you even see that if you have commodity CPUs like you find in on AWS, GCP, if you take the premium CPUs, for example, from Intel, sometimes your vector search is like 40 times faster. Now, GPU-based vector search is way faster. Like the throughput is way higher. But now an interesting thing emerges, right? So the question is, what's your use case? Because in Weaviate, for example, if you take an Intel CPU, right? You can resolve one vector search query on a data set of 1 million. So it's like, that's not like a lot, but it's just a benchmark, right? So you can solve that, resolve that in about 3 milliseconds. If you're willing to no compression, no nothing, 3 milliseconds. So that costs you about $11 in US dollars, about $11 a month. So now the question is, if you say, well, I'm happy with the 3 milliseconds because getting to 2 is almost, that's gonna get really hard, let alone 1. So if you say like, I'm happy with 3 milliseconds to get my result, then the question is about throughput. So how many because one CPU can do one operation, in this case in 3 milliseconds. So that means that in a second, you can do a lot of you can get a lot of vector results on one CPU, right? So because basically that is the number of milliseconds, so you get 1,000 milliseconds in a second, so you can just divide it by 3, so that's a lot. Now if you say that's not enough, then you say, well, then you have second CPU, so now you have not $11 but $22. The thing with GPU-enabled vector search is then it becomes, the throughput becomes higher, but a GPU, as you know, is very expensive. So then the question becomes like, what is the trade-off between doing it with a bit of memory and CPUs versus a GPU? So we are working with NVIDIA as well, and we're also talking to them about the integration, because the open source integration with Weaviate is just, you can add as many as you want. But the question that people ask us often is like, we don't want to have it faster, we want to have it cheaper. Because vector search gets on memory gets expensive quickly. So the fact of the matter is, and if I'm missing something, then I would love to learn. But one of the things that we're learning is that actually customers are not asking for faster, they're asking for cheaper. And with a GPU, it gets expensive very quickly. So I hope that answers your question. Yeah, and we have and that is in a memory index. We have a mix of a memory and a disk index, and we have a disk index. And that's important because fully in memory is the fastest. A little bit of memory and disk is in between, and then disk is slower. However, if you do it fully on disk, you don't have to pay for the memory. So that is way cheaper. So my point is that now what we see with people now going to production is that the use cases are very different, and that the needs that people have to make it reasonable. I mean, you can have a huge data set and make it super fast, all in memory, and then somebody has to pay like $2 million a month to run that. So a lot of our customers go like, yeah, that's great, but that's too expensive for us. So, which is understandable because it's $24 million just for a vector search use case. So doing a use case that costs you $2 million in memory on disk is more than 100 times cheaper. So now all of a sudden it costs you 150,000, right? And just by, so people are, that's an example. We say we are okay if it's a little bit slower, if it's more than 100 times cheaper. And they're not asking us, oh, we're not going to pay you 2, but we're going to pay you $4 million if you do it on GPU to make it even faster. The companies that want that speed, that is like just a few companies need that, right? Like, and maybe like Visa or something, those kind of companies. But for the rest, that's a very, very, very niche group. So what's also important last thing to add to that is like we also need to think about what does the user actually need? So now with the GPU acceleration, that's also a little bit, there's also some hype around it, like, oh wow, we can do even more and even faster, which is great. But then the next question is like, do people actually need that?